Welcome back. Now we are in a good position to set out a more quantitative, in-depth exploration towards the real-world networks. What are the degree distributions like in social networks? Is the Poisson distribution the right model for all those networks? What are the average clustering coefficients? Do they coincide with the prediction of Erdős-Renyi random network model? In this lecture, we will mainly discuss these two structural properties of empirical networks in reference to the random graph theory to see how well the theory captures the characteristics of the real-world networks. All right, now we know that the real-world networks are a small word. Take the movie actor network with over 30 million nodes, for example. The average path length is just 3.9, which is in dramatic contrast with the regular lattice systems, where the average distance scales as a power law with a system size, and the exponent is given by the inverse of the embedding dimension. The random network successfully reproduces such small word behavior, where the average path length scales as the logarithm of the network size instead of a power law. Then a related question is this: does small word mean that every node is tightly knitted one another? Comparing to the maximally possible number of links, real-world networks have far smaller number of links. In other words, the mean degree is much less than the total number of nodes. According to this table, the link density of the real-world network is indeed pretty low. If you look at the densest network of protein-protein interaction out of the examples presented here, the link density is still less than 1 out of 1,000. So the answer to the previous question is no. Even though the empirical networks are a small word, the interconnection between nodes is pretty sparse. That I talked about the protein-protein interaction network. Let us discuss the characteristics of this network based on the quantities we introduced so far. This undirected network has approximately 2,000 proteins as nodes and 3,000 physical interactions as links. Hence, the average degree is roughly 3, suggesting that a typical protein interacts with approximately 3 other proteins. However, this number is somewhat misleading. The breadth-first search tells us that the protein interaction network is not connected, but consists of 185 components shown as isolated clusters. The largest, called the giant component, contains 1,647 of the 2018 nodes. All other components are tiny debris compared to it. As we will see in the coming lectures, such fragmentation is common in model networks. Finally, a visual inspection reveals an interesting pattern. You might have noticed a few nodes that have exceptionally high degrees. Furthermore, those hub nodes have a tendency to connect to low degree nodes, giving rise to the hub and spoke character. This is a consequence of the degree-degree correlations. As we will learn in later lectures, this is an important structural feature that affects dynamical processes occurring on a network, such as the spreading of epidemic diseases, rumors, or political opinions. This is representative statistics of protein-protein interaction network of budding yeast. First, if you measure the path lengths between nodes by using the breadth-first search, they are narrowly distributed around the mean distance of 5.6, indeed showing the small world character. The local clustering coefficient as a function of degree is a bit noisy, but clearly shows an overall tendency of decrease with increasing degree, which is not consistent with the case of Erdős-Renyi random network, as we will see in the next slide. Another important observation, which I have alluded to when we watched the animation in the previous slide, is about the degree distribution. In double logarithmic scale, in spite of noise, the degree distribution is nicely fitted with a linear regression function. Here, several points along a horizontal line is an artifact called the finite size effect. Because we have roughly 2,000 nodes in this BPI network, the smallest non-zero probability is 1 over 2,000, which is 5 times 10 to the minus 4th, and cannot be lower than that. Instead, if we have a larger network by including newly found proteins and their interactions, this value can go further down to smaller ones. On top of linear fitting, an almost universal feature of the real-world networks is that there are nodes called hubs, whose degrees are exceptionally high. For a protein interaction network, these hub proteins are the proteins that maintain promiscuous binding with other proteins. The hub proteins might be clinically important target of drug discovery, or maybe the other way around, depending on purpose. If your intention is to screw up the protein-protein interaction network of pathogens, yes, inhibiting the hub protein may be an efficient antibiotic strategy, but when it comes to the human cell, targeting the hub protein may be dangerous because the hub proteins are very likely involved in many essential pathways. Now you have to worry about the side effects. Anyway, we call the presence of hub nodes as heavy tail or long tail. Sometimes you will hear the expression fat-tailed to describe a probability distribution that exhibits a large skewness or kurtosis relative to that of either a normal distribution or an exponential distribution. So if you recall Poisson distribution as a degree distribution of a random graph, this is a point of clear discrepancy between random graph theory and real-world networks. Unlike in Poisson distribution, which belongs to exponential family, the outliers are not negligible in this heavy-tailed distribution. Okay, let's first talk about the question mark in the previous slide. In addition to the small world nature and the Poisson degree distribution, another important structural signature of random network is the low clustering coefficient, which partly justifies the use of geometric series when we computed the average path length in the previous lecture. If you recall the definition of the local clustering coefficient, your delta is the number of triangles or closed triplets, if you will. Now, if you look at a single node and its k immediate neighbors, the number of triangle is nothing but the linking probability times all the possible links among the k neighbors. So the clustering coefficient is simply given by the linking probability itself, or the mean degree divided by the network size. Here we have 2 points to remember. For a given mean degree, the clustering coefficient of Erdős-Renyi graph is inversely proportional to the total number of nodes, and so becomes negligibly small as the network size becomes sufficiently big. Moreover, the clustering coefficient of a node in Erdős-Renyi random graph has no dependence on its degree, which shows a stark contrast with the real-world network. As you see here, the average clustering coefficient C divided by the mean degree K should be inversely proportional to the network size in random graph. But the empirical networks here of different sizes have a more or less constant value of average C over average K. The average clustering coefficient of the internet, science collaboration, and protein-protein interaction networks all show clear deviation from the prediction of random graph theory. Moreover, for the degree dependence of the local clustering coefficient, the real-world networks presented here unanimously show the decreasing, more or less decreasing behavior, right? With an increasing node degree, which again contradicts the random graph represented here as green lines. Okay, so the relevant question along this line of discrepancy is how we incorporate the relatively high clustering coefficient and the small word property shown in empirical networks. Duncan Watts and Stephen Strogatz proposed a protocol to generate the small word network with relatively high clustering coefficient. Starting with n nodes arranged along a circle, they gave an edge to the nearest and next to nearest neighbors, both on the right and left-hand side, so that every node has a constant degree of 4. Now they introduced the rewiring probability P. Rewiring takes place as follows. For every node I, take each edge connecting node I to its neighbors on the left-hand side or on the right-hand side, either left or right-hand side, and disconnect the edge from the end node and reconnect it to a randomly chosen node with probability P. To this end, we generate a random number uniformly between 0 and 1. If this number is less than the designated value P, then we perform rewiring like this. Otherwise, we keep the edge unchanged. So after full turn of rewiring trial, according to the probability P, every node still keeps degree 2 at least. An important point here is, before this rewiring starts, the initial value of clustering coefficient is 1/2, which is quite high compared to the case of Erdős-Renyi random network. It may be a good exercise for you to check if it's really the case by using the definition of the local clustering coefficient. Now, as we increase the rewiring probability from 0 to 1, many long-range connections would be formed, and the regular graph becomes more random. And it is not difficult to see these long-range edges will dramatically decrease the average path length of the network. At the same time, the clustering coefficient is still high, as long as the probability P gets not too high and the rewiring doesn't much mess up the whole network. Eventually, when P approaches 1, so all the edges are randomly rewired, then the resulting network would achieve the structure close to the ER random graph. Although it's not exactly the Erdős-Renyi graph because of the truncated degree distribution. And the clustering coefficient is now 4 over the network size, which is almost 0 when n goes to a big number. Eventually, the Watts-Strogatz model at some intermediate range of rewiring probability P shows both small word behavior and high clustering coefficient. As shown here, the clustering coefficient stays at the same level as the original value up until the rewiring probability reaches 0.01. At the same rewiring probability, the average path length quickly falls near to the asymptotic value of log n over log of mean degree, recovering the small world property of the Erdős-Renyi random network. Similar results can be obtained if we start from other regular lattices, such as square lattice, instead of a one-dimensional ring of nodes. Again, to summarize, though the random graph theory was successful in explaining the small world nature of real-world networks, here, it does not seem to correctly reflect the tendency that your friend's friend is also your friend, as you see here. Such tendency of Erdős-Renyi graph is negligibly small, which is not the case in reality. A friendship network is not automatically transitive, but human society still keeps high clustering coefficient. So to remedy this situation, Watt-Strogat's model came and provided an insightful view to the high clustering coefficient observed in real networks, which is great, but it could not explain the prominent discrepancy observed in degree distribution. Actually, this fat-tailed degree distribution is not limited to the protein-protein interaction network. As you see here, the Poisson distribution, indicated by these dotted lines, it significantly underestimates the frequency of both high-degree nodes and low-degree nodes. It predicts a larger number of nodes in the vicinity of the mean degree than seen in real networks. That is, in real-world networks, we see degrees that are orders of magnitude higher than the mean degree, which are forbidden in random graph theory. Then how do we model this linear behavior? The degree distribution of real-world networks are often modeled as a power law. People use a little fancy-sounding jargon, scale-free network, as often as power law. Then you might ask, what's the point of learning random graph theory if it's not an adequate theory of real-world phenomena? My answer to that question is actually another question. Why do we bother learning Newton's equation of motion for frictionless, idealized, free-falling particles? Nothing in real world moves like that. But starting from such an idealized and unrealistic system, we could send a rocket to the moon. Likewise, random graph theory is the base camp to explore the real-world networks. It's a reference theory. People do not make friends with others at random. Much of the human behavior is constrained and restricted because of customs, laws, and other cultural traditions. From the discrepancies we have discussed in this lecture, we learn and will try to come up with more inclusive and comprehensive theoretical framework. And in order to identify these deviations from the pure random component, we need to understand how would a particular property look like if it is driven purely by a random process. Here is another example of scale-free network. World Wide Web is a huge directed network composed of over 6 billion nodes and keep expanding. As you see, there are hub nodes which are heavily connected to other nodes. And these close-up images reveal the presence of a few highly connected nodes or hubs that signifies a scale-free network. The degree distribution is indeed given by a power law fitting function. In the next lecture, I will discuss general, more broad implications of this power law with a little mix of critical phenomena in physics and universality of network characteristics. Ciao.